Welcome back to the Oxford Mathematics Public Lectures Home Edition. My name is Alain Gorielli, and I'm in charge of external relations for the Mathematical Institute. As usual, special thanks to our sponsors, XTX Market. XTX Market are a leading quantitative-driven electronic market maker with offices in London, Singapore, and New York. Their ongoing support is crucial in providing you quality content. It is a great pleasure for me to welcome today my colleague, Jon Keating, who is the Sedleyan Professor of Natural Philosophy at Oxford University. As you may know, the Sedleyan Professorship is the oldest scientific chair in Oxford and is dedicated to applied mathematics. Jon was elected to this chair 2 years ago after an illustrious career at the University of Bristol. He has broad research interest in quantum physics, random matrix theory, and its unlikely connection to number theory through the Riemann zeta function. His research is truly fascinating as it draws connection between fields that are apparently disconnected, and I've been always impressed by Jon's originality and clarity of thoughts. Continuing in the same vein and exploring unlikely connections, today Jon will take us on a wild ride of extreme events and explain to us how the heights of an explored mountain, gold medals at the Olympics, quantum billiard, machine learning, and prime number are all somehow connected. So thank you very much, Jon, for doing this. Please start now.
Well, let me begin by thanking Alain for the kind invitation to give this lecture. What I'll be speaking about is a collection of problems which superficially may seem to have no connection, but which I shall argue are linked by a mathematical thread. And it's that mathematical thread that will be the main focus of the talk, rather than any one of the individual problems that I shall speak about and that are connected by it. I'd like to begin by inviting you to imagine that you're hiking in a mountainous terrain, rather like the one shown in this photograph. On your hike, your goals may be to climb one of the peaks that you see shown here, perhaps to walk along a ridge from that peak to neighbouring peaks, down from the peak and then back up to a neighbouring peak. Or it may be to descend all the way down and find a dip where water has collected and a lake or a pool has formed in which you can swim or where you can skim stones. Mathematically speaking, you're visiting what we would call critical points in the height of the Earth's surface. So critical points might be a local minimum. That's a point where a step in any direction takes you upwards. And that's the sort of place where a pool or lake may form as water collects. Different type of critical point would be a local maximum. That's a point where a step in any direction takes you downwards, and the peaks that you visit would be examples of those. And finally, there are saddle points, so points which are a minimum in one direction and a maximum in the other direction, and you would encounter these on the ridge between two peaks. So, your hike may take you to these various critical points, but perhaps your goal is more ambitious, perhaps you're more adventurous, and your intention is not to climb any old peak, but in fact to climb the highest peak in this vicinity. And some of you may recognise that to be Ben Nevis, which is shown there in the background. Much of this talk will be concerned with that kind of problem. The problem of identifying, finding the highest peak in some problem that's on some surface that looks like the one that I'm showing you here. Now, in terms of mountains, you may think this is a little artificial. We know where the highest peaks are. We have maps that show us that, and we even have GPS. But many of the problems that I shall be speaking about later are not of that kind. We don't have an identification in advance of where the highest peak is, and our job may be to find it and maybe to understand how high it is likely to be. And so I'm showing you this more for illustrative purposes, but I think it conveys the message. Now, there's another message that I want to convey from this picture, which is that looking at it, you may form the impression that the height of the Earth's surface in this vicinity is a rather irregular and random function of the position on the Earth, position where you are. So knowing your position doesn't necessarily mean that you can automatically deduce what the height of the Earth's surface would be. This terrain here is seemingly random or irregular. Put another way, if you know the height of the Earth's surface at one point in this terrain, it doesn't automatically tell you what the height of the Earth's surface would be some distance away or in some other direction. So that means that we want to model the height of this surface as being random. Now, there are many ways to do that, but the simplest one would be to assume that the height of the Earth's surface in that photograph is described by a normal distribution or a bell-shaped curve as shown in this picture. So there is an average height, that's the center of the distribution, the highest point in the graph there, and then the probability or likelihood of finding heights much greater than the mean decay rapidly as a function of height, and likewise the probability of finding very low heights decays rapidly as you go away from the mean. Now, I should say you could criticize this as a model for heights in mountain ranges. That's not my point. And in fact, the examples I'll be showing you later are ones where we do believe that this is the right way to model a distribution of heights. But just for the moment, let's take this to be the distribution of heights in the mountain range that I showed you. The questions then that you might ask, and these will be the ones that I should be focusing on throughout the talk, are in a situation where the terrain can be modelled by a random surface with a normal distribution of heights, a bell-shaped curve of heights, how effective can we expect methods to be for locating the highest maximum, that is the peakiest peak, or equivalently the lowest minimum? How high should we expect the highest maximum to be? You're given a random surface, do you expect exceptionally large heights to appear? How does that depend on the total number of peaks in the surface? And finally, to what extent do we expect these answers to depend on the dimension of the surface? The Earth's surface is two-dimensional, but the examples I'll give you later, at least some of the most important ones, will concern surfaces that have a vastly higher number of dimensions, thousands, millions, or billions. How do we expect random terrains to look like in very high dimensional spaces? So let me give you a few more examples just to whet your palate. Here you see the surface of the sea. Now, in fact, it turns out that the normal distribution is a very good model for the distribution of heights of the surface of the sea. And here, as is painted, the surface is rather irregular, rather random. So if you were sailing the boat shown in this picture, you might well wish to know how high is the highest wave you're likely to encounter, or how deep would be the deepest trough you might descend down into. In particular, how would that depend on the length of your voyage? As you encounter more and more waves, do you expect to find larger and larger highest waves? Or does the problem not depend too much on how many waves you're likely to encounter on your voyage? Here's a second example, and this comes from quantum mechanics. Quantum mechanics is also a wave theory. In this case, it's a wave theory of how things move. So the system I want to consider is a point particle moving inside some domain and bouncing off the walls. Think of it as a billiard ball bouncing around inside some billiard table. But in this case, the billiard table has a cardioid shape. What you see there is one trajectory of the billiard ball, and it's highly irregular. The motion inside the cardioid is chaotic. What you see on the right is a quantum wave function for this self-same problem. So this describes the quantum mechanics of the motion of a billiard ball inside a cardioid-shaped billiard table. You see the peaks of the wave. In fact, what's plotted here is the square of the wave. So half of those peaks will actually be deep minima reflected back upwards by the act of squaring the wave function. But physically that's the right thing to do, because the square of the wave function in this case gives you the probability of finding the particle at a given place or in a given vicinity. So you might well wish to know, how high is the highest peak of this wave function likely to be? Are there places where we might expect to find vastly higher probability of finding the particle than other places? How much does the height of the highest peak in this wave function depend on the total number of peaks that you see there? As we look at wave functions with more and more peaks, do we expect to find places or positions with increasingly high probability, and how does that depend on the number of peaks? Well, these are the sorts of questions I want to consider. And to start with, I want to consider a warm-up question, which has nothing to do with waves, nothing to do with mountainous terrains. It's a rather more elementary question, but I want to argue it captures much of the spirit of the problems that I've discussed so far. So the question I want to discuss is, in the Olympics, should we expect the number of gold medals won by a country to be proportional to the relative size of that country's population? So I'm focusing on gold medals here because they do signify extreme ability. One gets a gold medal for running for being the very fastest person. One of being an extreme of speed. One gets a gold medal in the javelin for being the person who can throw the furthest. Teams get gold medals in synchronized swimming for being able to swim in the most synchronized way in the competition. So gold medals signify or measure extreme events. And the question is, does the number of gold medals that a country wins, should we expect it to be proportional to the population of that country? Well, this question was picked over in the press after the 2012 Olympics and the 2016 Olympics, and the following was the sort of analysis that you found in many articles throughout the press, at least the British press. The argument went that Great Britain had a population of roughly 65 million and won in the 2016 Olympics 27 gold medals. The US had a population of roughly 320 million, that's about 5 times the population of Great Britain, and won 46 gold medals, so a little under twice the number. China had a population which was roughly 20 times that of Great Britain, and yet it won about the same number of gold medals. Japan, a population about twice that of Great Britain, yet won half the number of gold medals that Great Britain did, not twice the number. So the articles where one found this statistical analysis carried out, the conclusion drawn in those articles was that Great Britain had done disproportionately well, and that the country had done better than should have been expected on the basis of the size of its population. So the question I want to address is it true that the number of gold medals you expect to win is proportional to the size of the population? Going back to my questions earlier, is it true that the size of extremes, highest peaks, highest waves, are proportional to the total number of waves. Here's another more careful analysis of the Olympics. You find many of these on the web. I picked this one at random. Adjusting for population, these were the most successful countries at the Rio Olympics. So while the United States won more medals than any other country in the Rio Olympics, the article points out that its population is relatively high. And so this analysis took the number of medals won for all the various countries and compared them with the population size, taken very carefully from two sources. So this was a very careful analysis, and the two sources were the United Nations and the CIA World Factbook, a book which I confess I didn't know existed until I did this research to find this website. They divided the number of medals by the size of the population, and they found that the country which did best was Grenada, perhaps, which only won a single medal, but which has a very small population. And so if you divide the number of medals won by the population, it came out top. And the other countries that did well were the Bahamas, New Zealand, and Jamaica. In fact, and the US didn't do very well at all. Here is the list, or at least the top of the list that you find on this website. So Grenada did the best, and by some significant margin. And then the Bahamas, New Zealand, Jamaica, Denmark, Croatia did very well, Slovenia, Azerbaijan, Georgia, Hungary, Bahrain, Lithuania. Great Britain comes down this list. It's about 3/4 of the way down there. And so didn't do spectacularly well, according to this analysis, but did much better than other big countries, certainly much better than the US, China, Japan, etc. But is this a reasonable analysis? Is it the right way to level the playing field to divide by the total size of the population? Well, there are various different answers you can give to this. Here are two of them, two different opposing perspectives, both mathematical. One mathematical perspective is that Great Britain did do disproportionately well, and that you should normalise the data in order to level the playing field between countries of different sizes by dividing by the population size. And here's how the argument goes. So my first answer is yes. Just let's idealise. Let's consider an Olympics involving one event and two countries. And let's say the populations of the two countries are A and B. One of the people in these combined countries has to win the gold medal. And let's assume that there's no bias, that the person who wins, that one country is not, on average, athletically more capable than the other country. And so the likelihood of that person who wins being in one country, in the first country, is just A, its population, divided by the total number of people. As if you pick somebody at random from the A plus B people in the combined populations, there's a probability of A over A plus B that you'll pick someone in the first population. And the probability that the winner, whoever she is in the second population, in the second country, is, well, it's the fraction of people of the total combined population in that second country, B over A plus B. And so the ratio of the two is A over B, the ratio of the two probabilities. And so this would suggest that indeed normalising by or dividing by the population size is the right thing to do, the right way to level the playing field. But I would argue that this isn't the most accurate model of how the Olympic Games works. The Olympic Games doesn't involve competitions between all members of the populations of the various countries involved. I've never been involved in the Olympic Games, for example. So I would argue that a more accurate model of how the Olympic Games works is it's really a competition between the fastest person in the first country against the fastest person in the second, or the person who can throw the furthest in the first country against the person who can throw the furthest in the second country. So I would argue a better way to analyse this would be to ask, if you take a population, a country, how fast is the fastest person likely to be in that country? Or how far can the strongest person throw their javelin? So if people's sporting abilities, speed, strength, stamina, have a normal distribution and are independent of each other, out of a population of n people, how fast or strong is the fastest or strongest person likely to be? And I would argue that this is a better model for the people who enter at the Olympics and actually take part in the competition. So mathematically speaking, we should take n numbers, draw them independently at random from the normal distribution. So we weight the numbers with a probability that's given by the bell-shaped curve or the normal distribution. And we'll take that distribution to have mean mu, that's the value at the center of the distribution, and variance sigma squared. So sigma is the width of the bell-shaped curve. And the question then is, what's the distribution of the largest of these numbers? How large do you expect the largest one to be? And the answer turns out to be the following one. So it's given by this equation, which I show you in blue there. If you like equations, you'll be able to unpick this very quickly. But if equations are not quite your thing, let me unpick it for you. So the equation says the following: to compute what you expect to be the largest of these n numbers, you take the mean, the center point of the bell-shaped curve, and you add on to that something. You add on something because, of course, the largest is very likely to be larger than the mean. The amount you add on is proportional to the width of the bell-shaped curve. That's no surprise. If you take a normal distribution with a greater width, you expect to find more large values. And then multiplying the width is the square root of 2 times the log of the number of samples we've taken from the distribution, log of n. Now, for those who know their logarithms, they'll recognise that this depends barely at all on n. The logarithm grows with n, it increases as n increases, but it does so barely at all. It's one of the slowest growing functions you can imagine. And we actually have here the square root of the logarithm, which grows even more slowly. Some of you may know that a sort of paradigm of rapid growth is the exponential. Well, the logarithm is the opposite of that. It's a paradigm of slowest growth, if you like. So this is the answer. And it's an approximation to the answer, rather. And it's a beautifully simple formula. And it tells you how big the extremes are likely to be. So this same formula tells us how fast the fastest person is likely to be. But it also tells us how high the highest wave is that we're likely to encounter in our boat. The height of the highest wave, if we assume a normal distribution of wave heights, proportional to the square root of the log of the number of waves that we encounter. So taking a much longer journey doesn't dramatically affect the height of the highest wave you're likely to encounter, barely affects it at all. Likewise, in our quantum problem, the height of the highest quantum amplitude, the highest wave point in the quantum wave, is proportional to the square root of the log of the total number of peaks that you saw in the picture earlier. So barely affected at all by the number of peaks. In fact, if you analyse this a little more, you find that typically you expect to get up to this maximum value, lots of numbers, and then this is the largest, and then so after this you get nothing. So it's not that you expect to see one outlier dramatically faster than other people, a wave that's dramatically higher than other people. In fact, you expect to see lots of waves up to about the height of the maximum, and then nothing. Or lots of people who can run close to the speed of the fastest person, but then nothing. And that, of course, accords with your intuition or your experience of the Olympics. There are lots of people who can run almost as fast as the fastest person. That's why races in the Olympics are exciting. You don't know exactly who's going to win. But the So you get lots of people close to the fastest, not one outlier who's dramatically faster than everybody else. So I should say that going back to the Olympics, I'm not arguing that this is how you really should model the Olympics. Please don't use this as a basis for betting on the next Olympics. Of course, what this means is the dependence on population is really rather small, and dependence on other factors is far more important. For example, facilities in a country's gross domestic product, or the tradition of coaching in that country. These are far more important effects than the population size. Let me put in the populations just to illustrate how slowly the square root of the logarithm increases. If you put in the population of China and into that logarithm and divide by the square root of the logarithm of the population of Great Britain, you get an answer that's almost 1. So barely any change between China and Great Britain in terms of the dependence on population size. Now here's a more accurate answer. This is a better formula, therefore more complicated. But let me unpick this for you. So this is actually a very accurate formula for the height of the largest, or the extremes in a normal distribution. We have what we had before, the mean, mu, center of the value at the center of the distribution. We have the term that we saw earlier, which increases extremely slowly with n. Depends like the square root of log n. And then we subtract off a term which depends not just on the logarithm of n, but on the logarithm of n. And this term actually decreases as n increases. So we have a term that's about constant, a term that does increase but extremely slowly, and a term that decreases but extremely slowly. And then there are some small fluctuations which I don't want to describe in this lecture. They're beyond the scope of what I want to discuss. Now, you don't need to remember this formula or any formula in this talk, but there's one aspect I would like you to remember, and that's the number here shown in red, the number 1. That number I do wish you to remember, because we're going to come back to that a little later. So we have this very accurate formula, and this describes very accurately heights of the highest C waves, heights of the highest quantum waves, etc. Now, you may argue that this analysis I've given you is too simple, because it ignores the fact that abilities, say, of people in sporting events aren't independent of each other. There are dependencies. If we consider the heights of people, one's height is to a good degree dependent on the heights of your parents. If you have 2 very tall parents, your height is likely to be taller than average. If you have 2 very athletic, fast parents, there's a greater likelihood that you too will be athletic and fast. How can we build this into our model? Well, here's an idealization of a family tree. It's very idealized, but it just focuses on the essentials. We imagine at the top of the tree a matriarch. It's the first generation, so to speak. And we'll imagine, just for the sake of simplicity, that matriarch has 2 offspring. Each of those offspring has 2 offspring. Each of their offspring have 2 offspring, etc. Now, the number 2 is not at all relevant here. It's just for illustrative purposes that I'm showing this. Nor do we have to assume that everyone has the same number of offspring. Again, I'm just doing this for illustrative purposes to keep the description simple. So, as one goes from a parent to an offspring, let's imagine that the offspring acquires some characteristic. But it doesn't acquire a characteristic perfectly. There's some variance in the degree to which they acquire that characteristic. So we'll assume that as you go from a parent to an offspring, you pick up a factor, an attribute, drawn from the normal distribution, the bell-shaped curve. So as you go down the generations, each person picks up from their parent an attribute which is drawn randomly from the bell-shaped curve. But let's imagine that your net attribute, your net ability, is the average of the attributes of all of your ancestors going back to the matriarchal figure at the top. So you see at the bottom there is a population of people, and at the bottom of the green line there is a person, and the attributes they collect is the average of the attributes acquired through all of the generations going back to the matriarch. They have a sibling shown at the bottom of the brown line, and they too pick up attributes from all of the generations going back, and they'll differ from their sibling only in the one attribute they've acquired from their parent, which is drawn at random and independently from the bell-shaped curve. So this is a way of combining inheritance with randomness. And the question is, if you look at the population at the bottom, what's the distribution of attributes? Well, it turns out that a beautiful fact about the normal distribution is that if you average lots of numbers from the normal distribution, the answer you get still has a normal distribution. So the people at the bottom in that generation shown at the bottom, the variation in attributes will be described by the normal distribution, by the bell-shaped curve. But they're no longer independent because, for example, the person at the bottom of the green line and their sibling have lots of ancestors in common, lots of attributes in common. So they will be more similar than people who are more distantly related from them. And the level of similarity will be determined by their last common ancestor. What in this case do we expect to be the highest of those attributes? Well, if we have n people in that population, here's a formula for the largest of those n numbers. And this is a formula that's people have been thinking about this for the last 20, 30 years. So this is relatively recently discovered formula. And the formula looks remarkably like the one I showed you earlier. In fact, it's almost identical. So building in dependence via a family tree barely affects the answer in terms of the size of the maximum, size of the extreme. The answer is almost identical. It differs only in one way, and that's that the thing that was 1 before is now a 3. But that's in a very small term. So this dependence is very small, but it is there. Dependence does matter, but only at this very low level, in this very small term that gets smaller and smaller as n increases. But it is there, and the difference is that you go from a 1 to a 3. Now this 3 is universal. It doesn't depend on the fact that I assumed 2 offspring or equal numbers of offspring. Anytime you have a family tree lying behind your data, you expect to get a 3 and not a 1. So that's a description of some of the mathematics that underpins extreme events. Now let me tell you about some of the applications. And the first application I want to describe is to freezing of liquids to form solids. So any material, if you raise it to a sufficiently high temperature, is a liquid. That means its constituent parts, the atoms and molecules that make it up, are free to wander around at random and explore various different configurations. Each configuration carries an energy. And so as you explore various configurations, you're exploring ranges of different energies. As you lower the temperature, you lower the range of energies that you can explore. Until you reach the freezing point, when the liquid becomes a solid, where the constituent parts are fixed in space, and that's because essentially they're stuck at the lowest energy configuration. So when you're freezing a material, you're finding the lowest energy configuration. Now there might be configurations with local minima, but you're finding the very lowest one. So when a liquid freezes, temperature is lowered, the configuration of atoms and molecules seeks the lowest energy arrangement. In many situations, this lowest energy arrangement is highly symmetrical and highly ordered. So, for example, if you melt some common salt, and then freeze it again, you know that you form crystals, and those crystals are highly ordered and arranged. And that's because the lowest energy configuration in that case is very well defined. There's a clear winner in the lowest energy configuration, and the system manages to find that every time. And that's why such systems have a very well defined freezing temperature, and why every time you freeze the system you get the same configuration in the solid phase. There are, however, materials where that's not the case, and examples would be a glass, the glass that you see perhaps in the window in your room, or the glass that's in my spectacles. And in these cases, the energy landscape is vastly more complicated, and there isn't a clear, obvious winning landscape when it comes to being the minimum energy. In fact, these landscapes are so complicated, they're rather like the mountain ranges I showed you earlier, or rather like the surface of the sea or the quantum waves. There are lots of possible different arrangements, all with more or less same local minimal energies, and finding the right one, an obvious winner, is difficult. So when the system, when you lower the temperature, the system explores and finds itself in local minima, and these, you might get a different minimum each time. You might be stuck in a different minimum each time, and there's no reason to expect that in the solid phase the configurations will be the same. They're certainly not highly ordered. So the question is, why do glasses have relatively well-defined freezing transitions? Here's a picture of a cartoon, if you like, of the energy landscape for a glass. This was computed by Chiara Camerotta, who's an expert on this area of mathematical physics. And you see that what I said, that there are many possible local minima. Your system explores this terrain. As you lower the temperature, it will get stuck in a minimum, but it may get stuck in a very high-lying minimum, and therefore have an energy much higher than the potentially lowest one it could reach. There are many local minima it can attain, all with different configurations. Now, this really is a cartoon because, in fact, this surface isn't two-dimensional. It has many billions of dimensions. And so you have to imagine what this random landscape would look like in an extremely high-dimensional space, not a two-dimensional surface as shown here. Does that help us? Well, it turns out that in very high-dimensional random landscapes, one gets some simplifying features very unexpectedly. One feature is that the saddle points with higher energies look more like maxima than those with lower energies. Those with lower energies look more like minima. So what that means is that the high-lying saddle points have many downward directions and not many upward directions. And this really helps you. You might be troubled that your liquid will, as it explores various configurations, end up at a saddle point with a high energy, but which looks very much like a minimum and might get stuck there for a very long time, and you might freeze in that configuration. But that doesn't happen. It turns out that saddle points where you may think you would get stuck, the higher energy saddle points look more like maxima, so you're more likely to fall down in the cascade of energies. Down to lower energies, and it turns out that most minima have low energies, and in fact energies close to the lowest. Not all of them do. There will be some minima that have high energies, but they're very rare compared to the ones with low energies. And the lowest energy configuration is only slightly sensitive to the size of the system, as we've already seen. And so this explains why glasses have a relatively sharp freezing transition. It's because of this phenomenon that you get lots of things, lots of local peaks close to the highest peak, if you're interested in the highest one, or the lowest, if you're interested in the lowest dip, if you're interested in the lowest. Lots very close to that. And the configuration you end up in may not be the absolute lowest, but its energy is not going to be far away. And so the freezing temperature is pretty well defined in these systems. And this explains a puzzle that has been troubling the natural scientists for a very long time. We can apply this understanding to a different problem that's troubling people currently. And this is the problem of machine learning. How do you train a machine to recognize or categorize images that it's not seen before? So the idea is you want to show your computer pictures of cats, lots of them, and train your computer to recognize what a cat is, so that if you show it a picture not identical to any of those it's seen already, it will still recognize it as a cat. So you put in lots of data into your computer, lots of pictures of lots of cats. Each picture of a cat contains lots of data. There are many attributes to a cat, many things you can measure that would reflect in the data that you put into your computer. So your job here is to take lots of images. Each of them contains lots of information, and you put this into a computer and try to use this to train your computer to recognize a new image to be a cat as opposed to a dog or a hamster. How do you do that? Well, you take all the data you've put in, which now sits in a very high dimensional space, because we're putting in a lot of data, and each point of data contains a lot of information. There are lots of parameters to vary, so this is a very high dimensional space. We input the data, and then we try to find a surface that sits as close as possible to all of that data. So this surface will necessarily be highly complex and lives in a very high dimensional space. It has to be complex because it has to fit lots of different looking cats. There are lots of varieties of cat. So we have this very random surface in a very high dimensional space, and we want it to be as close to all the data that we put in as possible. So we vary parameters that describe the surface and try to get it to match as closely as possible the data that we put in. Now, what does as close as possible mean? Well, it means that the distance between that surface and the data points that we're putting in has to be as small as possible. That is, we have to find the lowest minimum of distance. So the problem of machine learning is exactly like the problem of freezing of glasses. We're finding the lowest minimum. And it's therefore exactly the same as finding the extremes of random surfaces that we discussed earlier. And you can analyze it in the same way. So we're to find the lowest minimum, and this will train the machine in the best possible way, give it the best possible chance to categorize images that it's not already seen. So can you find the lowest minimum? Well, this is one of the great challenges of modern computer science, and every company interested in machine learning has teams working on this problem. It's the moon landing problem of machine learning, is how to identify the global minimum, the lowest minimum of the surface that you form to approximate the data you've put in. Well, it turns out there are algorithms that do that, and they work very well. In fact, the big surprise in this area is not whether you can find an algorithm. We have them. The big surprise is that they work far better than might have been expected. And this was the great puzzle to resolve in the area. So here's an example of the sort of surface you get in these machine learning problems. This is taken from a paper visualizing the lost landscape of neural nets. Neural nets are a description of these random surfaces that one gets in computer science in this area. You see the surface is highly irregular, and your job is to find the lowest minimum on this surface, and that's the best approximation to your data. Here's another illustration of what these surfaces look like. This is taken from a website, lostlandscape.com, where I should say you'll also find films that you can explore. And you see these surfaces are extraordinarily complex. They're pockmarked with local minima, with saddles, maxima. So as you explore this surface, you may well get stuck in the wrong minimum. You may well get stuck at a saddle for a very long time before you find that it really is just a saddle and not a minimum. And in these very high dimensional spaces, I remind you, saddles can look very much like minima. If this was a surface of 1,000 dimensions, in 999 dimensions, the saddle might be upwards, but in only one direction may it be downwards. So it's very easy to be fooled in these high dimensional spaces that a saddle is really a minimum. So it looks like this would be an intractable problem, but in fact it isn't, and the methods that people have work extraordinarily well. Why is that? Well, it turns out that it's the same understanding we've developed all along. In these high dimensional, highly complex surfaces, the structure actually works to your benefit in that the saddles that you see if you're high up look much more like maxima than minima. And so you're naturally inclined to roll down the landscape with your algorithm and not get stuck in high-lying minima, because there are relatively few of those. Instead, you're likely to find a minimum which is very close to the global minimum. You may not find the absolute global minimum, but you can quickly get to a minimum that's very close to it, and that's good enough for all practical purposes. So those are some of the examples I wanted to discuss, but let me finish with a final example, which is of a very different flavour, and this is the Riemann zeta function. So the Riemann zeta function is a mathematical object, a surface, which is designed to understand the prime numbers. So the primes are the numbers divisible only by themselves and 1. So here are the examples of the primes up to 100. And for thousands of years, humankind's been interested in the distribution of these numbers against all of the whole numbers. Are there any patterns amongst the primes? Are there any ways to predict where the next prime will come, etc.? So people have found a way to analyse the distribution of primes, and this involves the Riemann zeta function. So what's that? Well, if we take a number s, we do the following to it. We get 1, we add on 1 over 2 to the power s, plus 1 over 3 to the power s, plus 1 over 4 to the power s, plus 1 over 5 to the power s, etc. So if s is 2, this will be 1 plus 1 over 2 squared, which is 4, plus 1 over 3 squared, which is 9, plus 1 over 4 squared, which is 16, etc. So for each number s, we can put it into this sum and get an answer out. For some values of s, you have to work a little harder, but I don't want to go down that route. We have a way to get an answer out for every value of s. Now, just to make this a little more complicated, it turns out you don't have to take a number like 2 or 3 for s. You could take a complex number, something that's a combination of a number that we see in the everyday world and the square root of -1. So if you understand complex numbers, you'll know what that means. You put a complex number in for s, and the value out that you get will typically be a complex number. If complex numbers aren't quite your thing, think of it that s is really 2 numbers. You put 2 numbers into this device and 2 numbers come out. So how does this help you? Well, there's a remarkable identity due originally to Euler, which says that sum is in fact equal to a product, and the product is over all of the prime numbers. So the sum, 1 plus 1 over 2 to the s plus 1 over 3 to the s, etc., is identically equal to 1 over 1 minus 1 over 2 to the s times 1 minus 1 over 3 to the s times 1 minus 1 over 5 to the s, 1 minus 1 over 7 to the s, 1 minus 1 over 11 to the s, etc. And these are all the prime numbers that are appearing in only the prime numbers. So it was realised by Riemann that just as modern chefs love to do, you can take a nice dish and deconstruct it. Riemann realised that you can deconstruct this formula, that if you understand the behaviour of the Riemann zeta function, you can deconstruct it to get information about the prime numbers. So this is how we understand the primes, is via the Riemann zeta function deconstructed. So what does the Riemann zeta function look like? Well, it's a little hard to plot because of the fact that complex numbers appear. But one way to represent it is in terms of colours. So here's a plot in 2 dimensions. The coordinates of a point in this 2-dimensional plot are the 2 input numbers, or the 1 complex number, if you know what that means. So you pick a x and y coordinates of a point here, and x and y correspond to the 2 input numbers, and the output is represented as a colour here. It's not the only way to represent the Riemann zeta function, and I'll give you a different one in a minute, but this is the one that we'll focus on for the moment. So you have colours at each point, but some points are special. They're points where all the colours meet. And you see a collection of these down at the bottom of the picture. They lie on a straight line, a horizontal line at the bottom of the plot. And Riemann realised that these points where all the colours meet are very special. In fact, these are the points that really determine the distribution of the prime numbers. This is where the deconstruction really acts. He realised as well that there aren't just these special points on the horizontal line at the bottom. There are some others that lie away from that horizontal line, and he hypothesised that those numbers lie on a single straight vertical line. Now, he wasn't able to prove that. He guessed it and left that as a challenge for future generations. And that's the problem that we call the Riemann hypothesis. It's that these special points where all the colours meet and that aren't the points on the horizontal line at the bottom, in fact lie on a single vertical straight line. And we can't prove that yet. If you do come up with a proof and you're able to get it accepted in a reputable mathematical journal and accepted by the mathematical community, you win $1 million, because this is one of the problems issued by the Clay Mathematics Institute. It's one of the Clay Millennium problems. Here's a different way to represent the Riemann zeta function, and this is a way due to G.H. Hardy, who was a great mathematician in the early part of the 20th century. And he thought, what does this look like as you walk up the vertical line where you expect those special points to lie? And he found a way to plot that. It's called the Hardy Z function, and it's the curve in blue there. So this curve oscillates, it's like a wave. It passes through zero, and the zeros are precisely the points in the previous plot where all the colours meet, going up vertically. So the zeros of this curve, the points where it intersects the horizontal axis, are the Riemann zeros. And these are the points that are, as I say, identified as points where the colours meet. What's the Riemann hypothesis in this setting? Well, it's the statement that this curve, if you look beyond 10, so to the right of 10 on the horizontal axis, that all the maxima will be positive and all the minima will be negative. So if you find a maximum of this function of this curve that lies below the horizontal axis, that disproves the Riemann hypothesis. So that's one of the great challenges about this, about the Hardy Z function, this curve here, show that it has no negative maxima or no positive minima, and that proves the Riemann hypothesis. There's another question that people have asked about this curve, again going back about 100 years, and this is how big do the oscillations get in the Hardy Z function? I plotted the Hardy Z function in the top curve up to 60 and then down below from 1,000 to 1,050. You see the oscillations continue, they get more rapid, and the curve seems to get a little bigger, but not by very much, the oscillations. And Lindelof, about 100 years ago, suggested that perhaps the Hardy Z function increases as you go along the horizontal axis, the size of the oscillations increases, but as slowly as you can possibly imagine. I'm not going to state that more precisely, but Lindelof made a precise guess that said that the Hardy Z function does increase in the size of its oscillations as you go along the horizontal axis, but as slowly as you can possibly imagine. Now, people have tried to think about this, work on this for the last 100 years, and hard-won progress has been made, but we're very far from proving that. So progress has been slow, steady, hard-fought, but we're very far from proving Lindelof. However, recently, a different question has been put forward, very much in this spirit, which it turns out we can answer very precisely. And this is the question, not how big does these oscillations get all the way out and some long distance along the horizontal axis. What if we look over a short distance? So what's the largest value of the Hardy Z function between t and t plus 2 pi? Now, it doesn't have to be 2 pi, it can be any constant number, but I'm putting 2 pi here for illustration. So how big do you expect the largest value of the Hardy-Z function to be, its largest oscillation, in a range of length 2 pi? 2 pi is about 6. Well, as t increases, you get more and more oscillations of the function in this range. And so we have more local maxima, local minima. How big is the highest or how low is the lowest? Well, here's the answer. It turns out to be that this answer is identical to the answer that we saw earlier for the extremes associated with family trees. The number 3 appears, and the terms are exactly matching those that we saw in the formula for the extremes associated with family trees. Now, the history of this is that this formula was guessed by analogy with the family tree problem, and in the last few years, people have managed to prove it. So we now have very precise information, astonishingly precise, just over the last few years about the extreme values of the Hardy-Z function. And this has come about because we asked the right question in this setting, a question that does have a very precise answer that we can prove. And proving this relies on showing that there is a family tree-like structure to the primes. And people have been thinking about the primes for a very long time, but this new understanding has emerged only recently, that you can group the primes together in the way they contribute to the Riemann zeta function in a way that makes them look like a family tree. And using that fact then allows you to prove this formula. So by thinking about extremes, we discover new properties about the primes. And I should emphasize that it's inconceivable that one would have guessed this formula if one hadn't been thinking about all the other problems in extremes that I've been describing earlier. So let me finish with a summary. Questions relating to the highest maximum or lowest minimum connect many different problems, from water waves, quantum mechanics, the Olympics, through to how glasses freeze, machine learning problems, the efficacy of algorithms in machine learning, and through to the Riemann zeta function. And by identifying that thread, we've managed to make progress in recent years that I think wouldn't have been imagined longer ago. So the statistics of extreme values shows universal behavior. You get the same formulae appearing time and again, and this commonality is what allows us to make progress on a broad range of these problems. So it might seem that we've made good progress, and I think we're pleased that we have, but I want to emphasize that going back to the first story I told you, the mountain range, we're really still in the foothills of this analysis, of this line of research. It's very clear that there's much more that we don't understand that we do. And the great challenge now is to take this analysis and make it more precise in each of these separate applications, and to get more and more accurate methods for analysing these problems about extremes in the various contexts I've described to you today. Thank you.